Hi, this is Maggie from Design Code Debugger Pete. Welcome to the channel. Today we're going to look at a tiled scrolling background. I've created tiled backgrounds and scrolling backgrounds in prior videos. I'll link the videos in the description. In this video, we're going to create a smart, efficient, random tiled terrain for exploration. This program is called Random Terrain Forever. If I run it, you can see I begin with an 800 by 600 pixel window that has some terrain. This is randomized, but it's supposed to be grass, dirt, stone, and water. I am using a wonderful tile set called Flowers Tile Set from No Logo Games on opengameart.org, and I will include a link in the description. I've modified this slightly. I've added the stone and water, and I'm only using a few of the tiles in this program, and I've reduced their size. There is a tiny character who starts in the upper left and is controlled by arrow keys. This is the character from my class dash example, but I've changed the color so that it's visible on this background, and it's pretty much unrecognizable as anything. I hope you'll forgive that. If I press the arrow keys, I can move around in the screen. But when the character is within a certain threshold of the edge, I'll show you, the background expands. It expands in every direction and, theoretically, infinitely. And it's efficient. I'm expanding the map of the background, which is simply a 2D list of integers, and only generating a surface the size of the visible screen. So every time the background has to scroll, which it does when the character moves within a threshold amount of the edge, the program uses the map to create an 800 by 600 surface of what is currently visible. So let's look at how that's done. I have a background sprite that I use to manage all of the background drawing and movement. I like to encapsulate functionality into objects, and this fits in easily with the pygame game structure, so that is why I've chosen this approach. There is one background object responsible for managing the map of the terrain, creating the surface, and keeping track of what part of the terrain is currently visible. It will respond to a move message by recording a direction of movement or stop, and it has an update method which is responsible for moving the background and generating a new background image. Let's look at the details. Right now, there are 4 different terrain tiles that I'm using. I store those in a list that is part of the background sprite called tiles. Each is a tiny 25 pixel by 25 pixel pygame surface. And you can see how that coordinates with the terrain map. The terrain map is a 2-dimensional list of the integers 0 through 3, 0 for dirt, 1 for rock, 2 for grass, 3 for water. When I first create the background sprite, I create a terrain map the size of the visible window. For example, this window is 800 pixels by 600 pixels. So I will generate a 2-dimensional list that is 800 divided by 25, or 32, by 600 divided by 25, or 24. 24 rows of 32 integers each integer representing a kind of terrain, and that terrain will take up 25 pixels in the image. Here I'm showing you a randomly generated terrain map and the resulting terrain that is drawn. The first integer in the first row is 2, grass, and you can see a grass tile in the upper left. Then there are 8 ones, that's rock, and you can see 8 gray tiles to the right of the grass, etc. When I first wrote the program, I randomly generated numbers between 0 and 3 for each location in the terrain map, so I could focus on getting the infinite expansion and scrolling working. Once that was working, I made the generation of the terrain map more complicated by trying to make the terrain make a little bit of sense, generating mostly grass with clumps of different kinds of terrain inside it. Now, once I've created that initial terrain, which is called _terrain inside the background sprite, I generate the image by creating a surface and then looping over the terrain and blitting the correct tile to the correct location. This is relatively simple when we have a map that is the exact size of the window. We iterate over the entire list using a nested loop. But what about once it's expanded? Let's assume a much larger map, or to use the map we already have, let's assume a much smaller window. Suppose our window is just 100 pixels by 100 pixels. Then it would show only 16 tiles. Here's a version of the terrain map with a 100 pixel by 100 pixel portion highlighted, 16 integers in a square. This square's upper left is at row 6, column 8. The background object keeps track of the indices in the terrain map of the upper left tile in the window. So when we first create the window, that's 0, 0. But once the terrain has expanded, that's usually not going to be 0, 0. In this example, that would be 6, 8. That's stored in a field of the background called left top, so it's actually stored as 8, 6. If we look at the loops in the getSurface method, it's iterating from left top sub 1, that's the row that we're viewing, in this case 6, through 6 plus the height of the window divided by the size of a tile. That's always going to tell us how many tiles we need in that dimension. In this thought experiment, the height of the window is 100, so we need 100 divided by 25, or 4 tiles. So we'll iterate from 6 through 9, a tile from index 6, 7, 8, and 9. And the same for the columns. We'll start at 8. Again, we'll need 100 divided by 25, or 4 tiles. So 8, 9, 10, 11. So this method first generates a surface that is 100 pixels by 100 pixels, and then it iterates from the current left top location within the terrain map through 4 rows and 4 columns to generate exactly the part of the map we're looking at right now. This will get assigned to the sprite's image field. The old surface, if we were looking at a different part of the map previously, will be marked for garbage collection, so the memory will be freed. So at any point while this program is running, there is one background surface exactly the size of the window. Now let's look at how this scrolls. In the main function, in the game loop, I'm processing a key press by setting a variable called direction. If it's a movement direction and not stop, which happens when all keys are released, then I find out if the player is within the threshold distance of the edge of the screen. If they're not, I can just move the player within the terrain we're already viewing. But if they are within threshold distance of the window, then it's the terrain that's going to move. I send the move message to the background object, letting it know that it will have to generate a new image upon update. Let's look at how that works. Here are the 2 public methods in background besides init. You can see there's move. It just sets a direction field. The update method is called once every game loop, so if the direction field is set, update will do the actual moving. Update is where the growing and scrolling work is done. I have 5 conditions. If the player is moving up, L if they're moving down, L if they're moving left, L if they're moving right. The player can move in only one direction at a time, so that's why those are together in a serial if statement. If the player can simultaneously move up, down, and left, right, you'd want 2 separate if statements for those 2 directional pairs. And then at the end, I have if they aren't stopped, so if the background did move one of those directions, we create the new surface. That's the method we just looked at with the nested loop that generates a surface exactly the size of the window from the terrain. The directional conditions are quite simple. If the player is moving up, then if self.leftTop sub 1 equals 0, in other words, if we are at the top of the terrain map, then we must insert a row above the top of the map. We don't need to change left top because it is at 0, and we've added a new 0 row, so we're still showing the 0 row. If the player is moving up, but we're not showing the very top of the terrain, as in our thought experiment where we were at row 6, then we simply adjust what we're going to draw. We subtract 1 from left top sub 1, so if we were at row 6, now we're at row 5. If the player is moving down, and what is being shown is the very bottom of our terrain map, we must add a row at the bottom. We must also increase left top because we want to show that new row, so the left top is going to be 1 more than it currently is, essentially moving the window down over the terrain. Left and right are equivalent to up and down. If the player is moving left, and we're at the left of the terrain map, we must add a column to the left, but we do not need to adjust left top because the new column will be 0. If the player is moving right, and we're at the right of the terrain map, we must add a column to the right and add 1 to left top so that we shift our window over to the right one to show the new column. If the player is at the edge of what's visible, but it is not the edge of the terrain map, we simply change what is visible in the correct direction by adjusting self.leftTop. So for our example in our thought experiment, if the top left is row 6, column 8, and the player is within threshold of the top of the window and moves up, we simply change left top from being 8.6 to being 8.5. We then generate a new surface which includes row 5 at the top and row 8 at the bottom, instead of 6 at the top and 9 at the bottom. But if left top is 0, 0, and the player is within the threshold of the top of the window and moves up, we generate a new row and insert it at the beginning of the 2-dimensional list. we're going to redraw, but because our new row is row 0, we don't need to adjust left top. The new row will be the first row in what is shown. Generating a new row is easy. We just generate the correct number of tiles and either append them to the end of our two-dimensional list or insert them at the beginning of our two-dimensional list. Generating a new column is a little more involved because we must add a new element to each inner list. If we're adding a column to the left, we insert a new element at index 0. If we're adding a new column to the right, we append a new element to each row. I hope you found this example of a relatively efficient, infinite, randomly generated tile-based background interesting. The code and assets are available for you in my GitHub repository. There's a link in the description. As always, have fun and keep coding.